So hi, my name is Frank, and today I'm going to talk to you about our system Splinter, which allows users to privately query public databases with sub-second latencies by splitting their query into multiple parts. This is joint work with Catherine, Shafi, and Vinod from MIT and Matei from Stanford. So every day, users perform searches on web services. For example, they might search Yelp for dinner options near Cambridge. They might search for directions on Google Maps, and they might search for flights on Kayak or Expedia. However, these searches leak sensitive information, and web services can use this information to perform malicious activities. For example, travel sites like Expedia can charge more for frequently searched flights. Just by having this data, companies can sell it to third parties. And finally, even if the service were honest, server compromise can leak personal information collected by these searches and queries. One naive way to solve this issue is for the user to download the database from the service and perform the queries locally on her machine. However, these databases, like the Yelp database or Google Maps database, are usually hundreds of megabytes, and the user has to re-download any updates, which leads to a high communication cost. This is especially problematic for users on mobile phones. So the question is, how do we build a practical system that can keep users' queries private? To accomplish this with our system Splinter, we consider a slightly modified setting with more servers and replicated databases. So more formally, Splinter has two principals, the user and multiple autonomous providers who each have a copy of the same public database in the clear. We assume at least one provider does not collude with the others. And on the web, many databases are public, such as OpenStreetMaps and flights data, and for efficiency, they are commonly replicated across many providers. And also, unlike in the naive approach, we aim to push some computation to the providers. So it's pretty easy for a provider to host OpenStreetMaps, and when a user does a search query, she can connect to her 2 or 3 favorite providers. So what happens in Splinter? A user splits her query into multiple parts and sends them to the provider. And each provider processes its share of the query on the database records and then sends back a response. The user then takes all the responses from the providers and combines them to get the result without the providers learning her original query unless all the providers collude. So in Splinter, our queries have low communication costs, computation, and number of round trips, which allows us to achieve practical performance. Our design is built on a recent cryptographic primitive called function secret sharing, which I'll talk about more later, that helps us achieve this. Now I've given you an overview of Splinter. I want to more explicitly state the threat model. The data on the providers is not sensitive and in clear text. The providers are passive adversaries, and they try to learn the user's query, but they cannot tamper with the query or the data. And we assume at least one provider does not collude with the others. Earlier, I talked qualitatively about Splinter's practical query performance, but here are some key performance numbers. We have response times of less than 1.6 seconds for databases with millions of records, such as the New York City map and US flights. And we have up to an order of magnitude fewer round trips than prior systems that use private information retrieval and garbled circuits. And this means that Splinter is the first system that can keep users' queries private while achieving practical performance for many current web applications. We achieved this performance with these key contributions. So Splinter is built on a cryptographic primitive called function secret sharing, FSS, that divides queries into opaque shares. We design new protocols to run complex queries, such as MAX, TOPK, and disjunctions over FSS. And we also have an optimized implementation of the FSS protocol using the AES-NI hardware instruction. And we also use one-way compression functions to reduce the number of instructions in the protocol. So here's an outline for the rest of the talk. I'll talk about what queries Splinter supports and how we execute them, and then I'll move on to the implementation and evaluation. So here's the query format. So Splinter supports a subset of SQL, specifically projections, limiting filters, aggregates, and no joins. We support queries in the following format. Select multiple aggregates or projections from a single table where certain conditions hold, and group by or order by multiple expressions with a specific limit. And it's important to note that Splinter's goal is to keep the sensitive information in the condition private. And in the next slide, I'll show what conditions Splinter supports. Splinter supports 3 types of conditions in the query filter. And the following table is important because the algorithm that Splinter executes for query aggregates depends on the condition type. The 3 conditions are equality only, intervals, and disjoint ORs. The form of the condition is in the right column, and E represents a column name, and CI can be an equality or interval condition. As I stated before, Splinter is the first system to use function secret sharing FSS as a building block for private queries. So before we describe how we execute queries in Splinter, I'll describe some important features of FSS. So the goal in FSS is to evaluate a function in a distributed fashion without the providers learning information about the function. So how does this happen in FSS? So first, a function is divided into k shares, and the shares have the following properties. Each share can be evaluated quickly. The sum of the shares evaluated on an input is equal to the input evaluated on the original function. And given all but one share, someone cannot recover the original function f. There are efficient constructions for FSS for 2 specific cases. First, point functions, which is a function that evaluates to 1 if x is a specific value and 0 otherwise. And for interval functions, a function that evaluates to 1 if x is between 2 numbers and 0 otherwise. So to better understand how FSS works in the context of Splinter, I'll start with a count query. And suppose we want to know the number of flights for a certain route. So for simplicity, let's consider a subset of a flight database with 2 columns, route and price. And each provider hosts a copy of this database. So suppose we want to count the number of flights where the route is 5, but we don't want the provider to learn that we're querying for 5. For reference, the answer to this question is 2. So how does Splinter perform this query? Well, we first need a function that evaluates to 1 if the input is 5 and 0 otherwise. Then the user uses FSS to convert the function into function shares for the number of providers. And in this example, there are 2 providers. Some important properties of the function shares, f1 and f2, are f1 of x plus f2 of x equals f of x. And having either f1 or f2 does not reveal any information about f. So each provider applies its share to each route in the database. And it's important to note that each provider has to scan through every entry in the database, or else we leak user information. And here are some example values that will be output by the function share. And all the operations are done modulo integer field, but we use negative numbers for our illustration purposes. Then each provider sums together the outputs of the evaluated function shares and sends them back to the user. In this case, one provider sends back 21 and the other sends back negative 19. And the user sums them together to obtain the answer to a query. So why does this work? So recall that f1 of x plus f2 of x equals f of x. So this means in our example, given our function f of x equals 1 if x equals 5, across providers, the values will sum to 1 if the route is equal to 5. And since f of x is equal to 0 if x is not 5, across providers, the values will sum to 0 if the route is not 5. So now suppose that we want to perform a sum query so that we can find the average price for a specific route. So how do we do this? It's just an extension of count. So we use the same setup, except we do a sum price instead of count in the SQL query. So on the providers, we do a similar thing as count and apply the function shares to each route record. Except in addition to evaluating the function share on each route record, we multiply the output with the corresponding price. And because FSS is additive, this essentially has the effect of scaling the matching records by the price. Then the providers add up all the results, send them back to the user, who sums them up and gets the final answer to her query. Now we've seen how to do 2 types of additive queries, count and sum. Let's look at how we do a non-additive query, min, with an equality-only condition. So consider the same table as the count and sum query, and now we want to find the price of the cheapest flight with route 5 and hide 5. So we use the same function as before, generate shares, and send them to the provider. However, using FSS is not enough to execute this query, but Splinter can circumvent this. The provider can use the public information in the user-provided query to form another query. More specifically, in our example, the provider performs select min price group by route. This query creates an intermediate table which has the min price for each distinct route. Because this table is created using a query based on public information, no sensitive user information is leaked. And computing this table takes linear time. Then we do the same thing as sum, apply the function shares to all the records in the route column in the intermediate table, and multiply the min price with the output of each function share. The provider adds all these values together and sends a response back to the user. So let's try to do a min query with a different condition type, intervals. So this query also requires us to develop new protocols. So suppose now we want to select the minimum price of many similar routes. And we can represent this using an interval condition, and we want to hide the values in the interval. So now I'll provide a high-level overview of the protocol. So first, each user uses the public information in the query to compute a sorted table T using the SQL query select route, price, order by route. Then the providers find the min price on power of 2 intervals in the sorted table T. And here, for illustration purposes and simplicity, we just show the price column in our table T. And for a sorted table of 8 values, we create size 2 up to size 8 intervals. Then the algorithm proceeds in 2 rounds. In the first round, the user finds the maximum and minimum indices where the route is between 3 and 6. And this requires 2 parallel FSS point function queries. And in the next round, the client selects at most 2 intervals of each size to cover the target interval and return the results. In this case, we select 2 from the sorted table T and 1 from the size 2 interval table. And this requires log n FSS function queries where n is the size of the database. And after the user receives the responses from the log n point functions, she combines the responses to find the min price in her route interval. So in the last few slides, I showed you how Splinter can execute additive aggregates like count and sum, and non-additive aggregates like max, min, and TOPK for equality only and interval conditions. I won't have time to describe how we do non-aggregate queries with destroying OR conditions, so I'll refer you to the paper for more details. So here's a table of the complexities for the algorithms described in the last slide, and n represents the number of database records. So some important things to note is that most queries can be done in 1 to 2 network round trips, and the computation time is at most O n log n for all queries, and communication costs are much smaller than the size of the database. We'll show in the evaluation how these translate into actual performance numbers. So for our implementation, we have an optimized FSS C++ library, which has 2,000 lines of code, a general query library, which has 1,500 lines of code, and we built 3 applications on top of Splinter, a Yelp clone, a flight search, and map routing. And code for our optimized FSS C++ library is available at this GitHub link. So here are some more information about the 3 applications that we built on top of Splinter and their datasets, such as number of rows and size, and some evaluation setup. So it's important to note that all these applications use real datasets. So here I'll present the SQL queries we perform on our case study applications. And our goal with this was to try to test various types of Splinter-supported queries on different datasets to show Splinter's expressiveness. So for Yelp, we counted the number of Thai restaurants, top 10 Mexican restaurants near me, and best restaurants from a subset of categories. For flight search, we look for an average price between a source and destination pair for a certain month and the top cheapest flights for a source and destination pair. And for map routing, we have to query a grid table and a transit node table because we use transit node routing, which is a method to do map routing that's compatible with Splinter. And for more information about this technique, I refer you to the paper. So here's just a table that summarizes Splinter's performance, and for a more detailed breakdown of the evaluation, I refer you to the paper. So there are a few things to note here. So we evaluated our system using 2 and 3 providers because the performance, especially the communication cost, differs based on the number of providers. As you can see, we can run certain queries with very short response times. For example, to query the top cheapest flights between 2 destinations takes less than 40 milliseconds on a real network. We can do map routing on a New York City map in under 1.2 seconds. And with that, all queries had less than 1.6 seconds of response times, and many queries could be run in hundreds of milliseconds. As you can see, also most queries had 1 to 2 network round trips, and all queries had communication much smaller than the size of the database. For example, queries like average monthly flight price and top 10 cheapest flights only take a few kilobytes. So although we're slower than running the queries natively, Splinter can perform common web application queries very practically. In the next slide, we'll show how Splinter compares to other schemes. So here we'll compare Splinter to a state-of-the-art PIR system by Olumofin et al., which is most similar to Splinter in terms of supported queries. So for similar queries, Splinter has up to an order of magnitude lower response times compared to Olumofin et al. And for Olumofin, the number of round trips is proportional to a log factor of the database size, which is about 10. And for Splinter, most queries only take a constant number of round trips and does not depend on the database size, and takes log-in only for a select few queries. So there's other related work in PIR systems and garbled circuits, but they all have much higher communication costs and computation costs, or both. So to conclude, I presented Splinter, which is the first practical system that protects users' queries on real datasets. We developed new protocols to execute complex queries over FSS and have fewer round trips and lower response times than prior systems. Thanks, and I'm now open for any questions.
Yeah, I'm also from NetApp. Nice work. So I missed the part that how you derive that F1 and F2. It seems like the F1 and F2 have to be different by conditions, right?
Yeah, so F1 and F2 is derived from using the function secret sharing. So we use function secret sharing to create the function shares F1 and F2. But I didn't go into details on what the crypto is behind that.
The result of F1 and F2 have to be pre-computed before the queries, or is it dynamically computed?
So F1 and F2 are just function shares. So you apply them to an input and there's an output. So the function shares themselves have to be pre-computed by the client and sent over. And this is essentially the client's query.
So if there is any update on the database, can you deal with that easily, actually, too?
And so if there is an update on the database, F1 and F2 are independent of the database. So if the database updates, for example, if it updates while you're executing the query, there's nothing we can do about it. But if the database is updated, then you have to make sure all the providers are in sync. And so you can use your common consensus protocol to make sure they're in sync. And then you issue F1 and F2 again, and then they can just run. But F1 and F2 are independent of kind of the database itself.
Can you elaborate more on the expressiveness of your queries?
Yeah.
Specifically, I had a question about the actual thing that you want to query. Was there a mapping, intuitive mapping to the SQL statement, or did you have to sort of change the SQL statement to the ones that you support?
Yeah, so I think so we did. This is. So I thought I had a backup slide, but so we went through kind of Yelp and Kayak and all these different sites, and most of them actually do equality and range queries. So for example, you can totally imagine if I want to search for flights, it could be a select flight number, min price, where kind of source where kind of route equals San Francisco to Boston or something like that. So we kind of map from what we would normally search into kind of what we thought would be a reasonable SQL query.
Thanks.
Great work. I think this is a significant advance in making private information retrieval more practical. My question is about the cost of actually running this in the cloud, because it seems to me much more expensive than just downloading it and running the queries locally, because now you use multiple clouds. Each cloud has to do at least a linear scan, so you have to pay for the compute. And then you have to pay for any storage accesses in case you're accessing each element from storage. That's really expensive. And I saw your datasets are pretty small, so it seems quite easy to just download them locally and service them locally. So I wonder, given that the cost is higher to run it this way, what are the incentives of using?
Yeah, so I think there's two parts to the question. One, you're saying kind of what is the cost? So in our paper, we actually run this on EC2 and look at the cost, which I didn't bring up here. And we saw that in our most expensive query, it took 0.02 cents per query. And so you can totally imagine like a price model where Google Maps offers a private version and charges kind of users $1 or $5 for 100 queries in a month, and they can kind of like receive a pretty high margin on that, modulo kind of engineering costs, et cetera, et cetera. And I think the question about databases being kind of relatively small, I think the problem is these databases, one, get updated, and two, kind of for mobile phones, actually this is like a pretty big concern. Like when I look up on Yelp, I don't want to be like downloading like 50 megabytes of data every day, right? And so it's also easier to kind of make sure you're always up to date and get the most recent information.
Cool, thanks.
Marco Canini-Kaust. So this is very interesting work. I was wondering if you're familiar with the very recent paper, OSDI 2016, Royan, the system that uses SGX to provide the ability to answer to requests that execute on secret user data and executes on code that is not trusted by employing SGX.
Yeah, I am familiar with the work.
Okay, so I was wondering if you were to contrast your work with theirs in terms of the trust model and the capabilities, where would you see your work fitting in the space?
Yeah, I think they're different models because Royan uses Intel SGX, so it's already assuming like hardware trust. In our case, we're assuming kind of none of these hardware assumptions. We're just assuming kind of like the server will execute the code we tell it to execute. And I think our model is more focused on actually users issuing queries. So for example, like a query model, and theirs is about kind of like having analytics being analyzed in the cloud, as far as I can remember from the paper.
It's a form of query as well.
Yeah.
Right?
Okay.
In their case, I mean, the example they give is like running a machine learning application and having an answer from the predictive model, which relates to a query. But I understand that you have operators, specific SQL queries.
Yeah.
But I guess you're making different assumptions regarding what you trust, right?
Yeah.
Of course, they trust hardware. To some extent, you are trusting the fact that the database is basically partitioned, and that you can ensure that k-1 values can be gathered from the share function, but not all of them, right? Otherwise, it breaks the entire guarantees. Is that a correct understanding?
Yes.
Okay. And what will be in practice, why is this a relevant assumption that we can make? Like if I go to a Kayak, how is it that I can assume that none of their servers will collude?
Yeah, so I think the model isn't that you assume Kayak servers won't collude. I would say, for example, when you do flight search, you go to Kayak and then you go to Google Flights, or you go to Priceline, or kind of different providers that are independent. And so they all, for example, the US Flights database is public. So and so they would all host this. And let's say they all get it from like one data source, like ITA or something like that. And they make sure they're up to date or they're in sync with ITA. And so you would issue one to Kayak, one to Google Flights, and then get the responses back and combine them. So.
Okay, thank you.
All right, let's thank Frank.